In the previous video, we highlighted two key concepts when one talks about the network layer in a protocol stack, namely routing and addressing. We also indicated that IP, the Internet Protocol, would be our primary example of a layer 3 protocol. In this video, we introduce IPv4 addressing, and we also touch on routing in IPv4. When IPv4 was designed decades ago, they never expected the internet to grow to the size it has grown to. So they decided that a 32-bit address, 4 bytes, would be sufficient. In the spirit of local autonomy, they knew that they were going to assign a portion to a company, that would be the network address, and then the company could assign addresses to its computers in whatever way they deemed fit. So there would have been two fields, a network portion and a host portion. Network portion would be determined by some issuer of network addresses, and the host portion was completely up to the owner of that address, how they would use it. The question was, however, how to split these 32 bits. How many do you allocate to the network portion and how many do you allocate to the host portion? Because you may have huge companies who have many hosts, but you also have tiny companies who have not many hosts, but there are many such companies. So what they decided was to come up with a scheme that is known as a class-based scheme. The class-based scheme has since been dropped, but it's still useful to think about it. The class-based scheme was to be denoted using the initial bits of the 32-bit field. So this is pretty much like what we've seen in UTF-8, where the initial bits indicate how what follows should be interpreted. In this case, it looks slightly different, but you'll recognize the scheme. So what they said was, if we start with a 0, so if that very first bit there, right at the start of this 32-bit sequence, is 0, then it would be class A, and they would use 8 bits. That's the first byte for the address field. Now, obviously, if you're using a 0 to indicate that you are going to use an 8-bit field, or that the first byte is to be used, you've already used 1 bit. So that leaves you with 7 effective bits. The second option that was to be distinguished or separated from the first one by marking it with a 1 and a 0. And that would be a class B address. In that case, the split would be right here in the middle, 16 bits for the network portion, 16 bits for the host portion. However, we've already used up 2 bits, so for the network portion, that would leave you with 14 possible values. And then they continued the scheme. 110 would be where the split would be made at that very last byte. First 3 bytes to be used for the network portion, last byte to be used for the host portion. So class C address, in this case, 3 bytes, that's 24 bits used for the network portion, but 3 of them already used to indicate that this is a class C, and therefore 24 minus 3, 21 effective bits. So what that tells you is that in a class A network, you can have 2 to the power 7, that's 128 possible networks. Thinking about it slightly differently, about 128 companies can get a class A address. Similarly, for a class B, 2 to the power 14 network addresses are possible, so that would be 16,000 approximately. And with class C networks, with 21 bits available, it would be about 4 million companies, but every company would only be able to use 8 bits for its hosts. So with 8 bits for their host, that would mean they can address 256 machines. Not that many in today's conditions, but back then in the 1970s, there were no cellular phones, there were no pads, there were nothing of that kind. They basically had mainframe computers and mini computers. So nobody expected the growth that we've seen since then. Before we leave this class-based notation, they said, well, we've got a nice thing going with this bit pattern scheme. So 1110 would be a class D, and then finally they said 1111 would be a class E. Class E is something that they reserved for future use back in the 1970s. It's never been used, probably will never be used, but it's there, it exists. Class D is intended to be used for multicast purposes. Remember in the first video we said that you could add a router, specifically an interior gateway protocol router, and it would just figure out what its role is, what the addresses are. Well, it would multicast its presence to other networks or other routers on the network. The other routers will tell this router using multicasting how they can get or which nodes they can reach, and therefore using a sort of a broadcast mechanism. This is not broadcast to everyone on the network, it's just broadcast to the router group. So in that sense, it's a multicast mechanism. The Class D addresses do not have a host portion and network portion. It's an indication of which group you're talking to, and it's typically only used on your local network. It's not routed out. One of the next questions they had to think about was, how would they write down an address like this? It was possible to write down 32 bits, but that's not very user-friendly. The scheme that they decided to use was one where they would convert every byte to a decimal value and then write down these 4 decimal values separated by dots. It's known as dotted decimal notation, and the typical example of such an address would be something like 192.168.3.1. You can see the values of the 4 bytes. You can see that they are separated by dots. And one of the interesting things is if you convert the first byte to a binary, you will see that it would start with 110. Whatever follows is not really important for our purposes right now. The fact that it starts with 110 immediately tells you that that is a Class C address. So taking any address whatsoever, you can determine its class by just looking at the first couple of bits of the first byte. Knowing that this is a Class C address tells us immediately that the network portion of the address would be those 3 bytes, and the host portion would be that final byte. For reasons that will become clearer a little bit later on, they also designed the notion of a net mask. A net mask is a mechanism that you use to indicate what portion of an address is intended to be interpreted as the network portion, and by implication what portion is to be interpreted as the host portion. If you are using a class-based mechanism, then it's obvious for a Class C address, the first 3 bytes would be used as a network address, or the network address or network portion, and the last byte for the host portion. However, suppose you have an address like, let's make it 10, and that's a decimal 10, 10, again decimal 10, 10, then it wouldn't take much for you to figure out that 10 starts with a 0 in the first byte. That means it's a class A address, and that means that the initial part, only that part, is the network portion, and everything else will be the host portion. The notion that they came up with is called a net mask, and a net mask marks every bit in that 32-bit field with a 1 if it's part of the network portion. So for this, it would be 1, 2, 3, 4, 5, 6, 7, 8. All 8 those initial bits of the first byte, all 8 bits of the initial byte, form the network portion. Everything else, and now it becomes a lot of writing, so let's just say 0, and just continue straight through. The 8 zeros to indicate that the next field is host-based, and the same for what remains, and also for the final byte. The long story short with these net masks is that for a class A network, you would expect the net mask to be 255.0.0.0. So the first byte indicates the network portion, the remaining 3 bytes form the host portion. The next possibility, class B network, net mask would look like that, because the initial part forms the network portion, and then 2 bytes remain for the host portion. And a class C similarly will look like this. Now, the obvious question is, if we know what the net masks are for every class of address, why do we specify it? That will become clear in the next video. Just remember that a net mask is indeed a value where you use a binary 1 to mark every bit that forms part of the network portion of the address, and a 0 for every bit that forms part of the host portion. It will always be a sequence of 1s followed by a sequence of 0s. There will never ever be a mixture of 1s and 0s that follow one another, except in this specific pattern. So this notion of local autonomy would mean something like the following. If your organization has been given the address, let's say 192.168.5. Now, if you look at the first 3 bits in that field, you will recognize this as a class C address. So that address is fixed. It's been given to you. You can't do anything about it, but you have control over the last bit, or the last byte. So you can number your computers 1, 2, 3, 4, and so on. But there are 2 special cases here. If in the host portion you put a 0, then what you are saying is, I'm talking about the address, the complete 32-bit address of my network. Usually this is referred to as the network address. Clearly it should be distinguished from the network portion of the address, which would be the first 3 bytes. Similarly, as a special value, if you put all 1s into the host portion. So in this example, the host portion is only the last byte, and in decimal all 1s would translate to 255. If you put 255 into that field, that's the broadcast address. That means the message that I'm going to send now will go to all the hosts on this network. To illustrate this with another example, if your given network portion is 10, Looking at the first 10 decimal. Looking at the first couple of bits will tell you that this is a class A address. It means you have control over the last 3 bytes. You can put in any addresses there, in numbers in there that you want to put in there to number your computers, all potentially 2 million of them. But there are, again, these 2 exceptions. If you say .0, in other words, you fill up the entire host portion with zeros, then that says I am talking about the full 32-bit address of my network, not of any host on the network. Again, we refer to that as the network address. And the broadcast address in this case would be the prefix 10 that's been given to you, and then filling up everything else with ones would mean that you get 255.255.255. So there's your broadcast address for this network 10. The place where you would use a broadcast address is sometimes you want to talk to everybody on the network, and therefore it makes sense to have a broadcast address. The network address is very often used in routing tables. Recall that in the first video we spoke about the destination of a certain packet, and a routing table in IPv4 would specify the destination as the address of a network to which you want to be routed. What happens inside that organization, how they're going to handle it, that's up to them. So in the routing table, you will use an address like this to say, how do I get it to that network? And then the organization who receives that address can use it for its own purposes. Perhaps I should let you in on a little bit of a secret if you don't know it yet. The address 10 will never be assigned to any organization. It is a so-called private address. So anyone in the world can use it, it's open, and it will not be routed across the internet. So if you want to build your own little network, you are free to use it, and other people also use it. So 10.0.0.0 is a private network to be used by anyone in the world whenever they want to. It's a class A address. In the B block, a range of addresses have been allocated for private use, and they are 172.16.0.0, and it goes all the way down to .31. In the C block, they've even been more generous. They've allocated 192.168. And here you can go from 0, you can have a 0 there, and you can go up all the way to 255. So 256 possible addresses in the C block that you are allowed to use for private use. They are not assigned by an ISP or by someone else. Anyone is allowed to use these. There are a couple of other addresses besides the broadcast notion and the network notion, other addresses that have been allocated for special use. And the two most important ones for our purposes right now are the following. There's an address 0.0.0.0. Now, obviously, that would be a class A address, but that's been allocated to refer to a computer who does not have an address yet. In fact, it is typical during, let's say, a DHCP request, where a computer requests an address, and it sends out a message that says, please give me an address. What does it use as the source address for its request? It will broadcast the request because it doesn't know who the DHCP server is, and the DHCP server can broadcast back, so this one doesn't need a specific address, but it needs to put something into the request field to say, this message is coming from this address. and that 0000 is used to refer to me as the sender who don't have an address yet. The other address also refers to one's own computer. It is 127.0.0.1. That is localhost. Sometimes people also talk about 127.0.0.0 local net, but localhost is the useful one here, and localhost refers to this computer. So if one program wants to talk to another program on the same computer, it doesn't have to figure out what the IP address of that computer is. It can just use the localhost value 127.0.0.1, and it would be able to talk to the other program on that computer. Let's look at these concepts in a practical context. Here I have a Microsoft Windows computer, command line prompt, and I am going to just enter the command ipconfig to see the IP configuration of this machine. So what you can see there is that the IPv4 address of this computer happens to be 10.1.2.132. You can see that this is one of the public or private addresses that we mentioned earlier that I'm using on my home network. You can also see that the net mask, the subnet mask, often also referred to as the net mask, is not what you would have expected for a Class A. It is 255.255.0.0. You can also see a default gateway there that we will talk about in a moment. So let's now look at a Unix computer, actually a Linux computer. In this case, the command is ifconfig, interface configure, and hitting enter, you will see that there are, just as we had in the Microsoft Windows case, a couple of interfaces. And here are two interfaces that are of interest for us, the Ethernet 0 interface and the local host interface. The Ethernet 0 interface, if you look at the second line just below the value, then you will see that the IP address of this machine is 10.1.1.15. So again, one of those private addresses that I'm using on my local network. You can see that the broadcast address has been completed as 10.1.255.255. So again, something strange going on there. We'll discuss that in the next video. And you will see the net mask is 255.255. In other words, while this is a Class A address, I am treating it like a Class B address. The first 2 bytes are part of the network portion, and only the last 2 bytes are part of the host portion. If we go down to the local host address, then there you will see that the address is indeed, as we've said, 127.0.0.1, and being a Class A network, you will see that the net mask is 255.0.0.0 as we would have expected. Now that we've briefly looked at IPv4 addresses, we can touch on the routing algorithm. The routing algorithm, as we said previously, is basically one that determines what is the next hop that the machine should send the packet to. It depends on where we want to begin to think about it. It is possible that the packet that we are looking at is actually at its destination. In other words, the destination address of the packet is the address of the router that we are talking about. And in that case, the packet will simply be sent up to layer 4 in the protocol stack, eventually as far as it needs to go to the application layer, most probably. The second possibility, if it's not intended for this router, it may be intended for the for this network. So how do we know whether it is intended for this network. Well, it's very simple. If we compare the network portion of the packet, and more specifically the network portion of the destination address used in the packet, and the network portion of this router that we are working on now, if they're the same, then it means it's on that network. It's arrived at its home network, at its destination network, and direct delivery is what will happen. It will just give it to the local network to deliver. Else, if that's not possible, it will consult its routing table. Remember that in our discussion of routers or routing in the previous video, we spoke about routing tables. So it will look it up in the routing table. And the routing table will tell it what the next hop is, and it will then send it off to the next hop, which would be a machine that is directly connected to it. But it's possible that there's no entry for that particular packet in the routing table. So what this will mean is we may have a default gateway that is being specified. Recall that on the previous screens where we looked at the Unix and Windows output, we saw that a next or a default gateway was specified. So if a default gateway is specified, we're just going to send it out to that default gateway. If no default gateway is specified, then IP will say, well, I've tried my best. I've done everything that I could do. I don't know what to do next. I'm just going to drop the packet, discard it, throw it away, get rid of it. It's gone. IP never tried or never purported to be a reliable protocol. It will try its best, but if it can't do it, then it's not going to do anything about it. It will just drop the packet. Again, to make this more realistic, let's look at the router that I'm using in my home network. What you will see being displayed is in essence a routing table. And if we start at the bottom, you will see that I have a Class C network, happens to be one of those private addresses in my home network. You can see that I'm talking about a network in part by the fact that the very last field, the very last byte in that address is a 0. So I'm talking about a network, and what this router says is if any packet arrives, that it should just be delivered via the Ethernet 8 interface. Similarly, for the one just above that, that is a different Class C address or a different Class C network that I'm running in my house. Again, you can see that the address portion of the host portion of that IP address is a .0, so again as a network address. And what this says is it's arrived, just send it out to its local Ethernet 9 port. There you can see the generic local host address, where it says if something arrives for the local host, just send it out via the local host interface, which is this computer. Immediately above that, you have the address, again a network address, but again one that looks slightly strange and that we will discuss in the next video. It's 10.1.0.0. Being a Class A network, we would have assumed that that would have been 10.0.0.0, but it's not. So as I said, we'll discuss that. And what this routing table says is it's directly connected to this router. Just send it out to Ethernet 9. That's where that network is plugged in. And the very first entry in this table is one that says if you want to send it to anywhere else. Now, why 0.0.0/0 means anywhere else, why that is the default gateway,
is also something that we will discuss in the next video. But that basically says the default gateway for this is 192.168.2.13. And just as an aside, if you want to get to that particular network, you can send it out via the Ethernet 9 port. This was the brief introduction to IPv4 addressing and a little bit of an introduction to routing. In the next video, we will look at subnetting. And you've seen an example of subnetting. My address 10 that I've used here as a Class B address, while it really is a Class A address, will be the topic of subnetting. We also just have to say that, as I said in the beginning, the whole notion of class-based addressing is really an old notion. It's useful to talk about it, but in many cases it no longer makes sense to talk about classes. And we will very soon introduce a more classless notion of talking about addresses.
Music